Hi, I'm Yu Yin from Computer Science Department of Columbia Engineering. My final project is the Chameleon 16 Challenge. First, there are some things to note that I summarized from papers and lecture. The first thing is that we can sample randomly in training stage and use a sliding window in testing stage. The second thing is that the Inception V3 structure works very well in this task. Also, the paper mentions that more magnification levels show no benefits, and the paper used two levels actually. The paper mentioned that the RMS drop optimizer works very well in this task. And another thing we need to note is that we need to balance cancer and the normal data. Also, data augmentation is helpful. And pre-process the data and extract the patches from the images. I use the method mentioned in the lecture. As in this slide, I first extract the patches randomly for the training data, and then for the testing data, I use the sliding window to extract all the patches in the image. When I do random sampling for the training and validation data, first I randomly select a tissue pixel. Then I elect the selected pixel to be the center, and then I sample 299 and 299 patches on level 4 and level 7 images, and label the patch as cancer if the center 128 has cancer. When I use a sliding window for test data, I just slide a 128 window through the whole image and extract the 299 and 299 areas surrounding it. So the question is, how can we balance the data set? I used the two approaches combined to balance the data set of cancer and normal data. The first approach is that I arbitrarily increase the probability of sampling the cancer region, and the second approach is oversampling. In order to increase the probability of sampling the cancer region, for part of the data, we first randomly select a pixel from tumor pixels in tumor mask instead of the tissue pixels. Therefore, we can ensure a certain amount of cancer data to be extracted in our dataset. And for oversampling, we just sample a large amount of patches and then delete the extra patches in the normal data. This slide shows my model structure. You can see that I used patches from two magnification levels to train two Inception V3 models. One model is for level 4 downsampled images and the other is for level 7 downsampled images. I average the probabilities given by two models to predict if a patch is cancer or not. And this slide shows the training and validation accuracy of the two models. After training for 30 epochs, the accuracy of the validation accuracy of both models is around 85%. The below one is the heat map my model predicted for one slide, and this one above is the ground truth. The red and pink regions in the heat map are predicted to be cancer, and we can see that there are two regions of cancer in the original slide, and in our heat map for this region, you can see that there are some red and pink patches, and but for the other region, the prediction is not very significant. Also, there are some noise in the heat map. To evaluate the models, I generated test patches from 3 slides, and I evaluated accuracy with test data for level 3 and level 7 model respectively. For the level 4 model, I get accuracy of around 85%, but for the level 7 model, I only got the accuracy for 59%. This shows that the higher resolution model works better actually, and it corresponds to the statement in the paper that we may use only one high resolution model to achieve decent results instead of 4 models. And now I will show you through my code. So this is my code for the project. And in the first part, I just downloaded the slide and tested the starter code with it. And these are all the starter code. And here I prepared the training data. First, I define a function to find the tumor pixels, and it's similar to the tissue mask function. And I use the function to select randomly from the tumor pixels. I save the data of level 4 and level 7 in different training paths. Here is the function that I use to extract the patches from the images. First, I select a pixel from the level 8 image. I used 15 slides to extract the training data and extracted 60 patches per level from each slide. To balance the dataset, if tumor exists, we ensure each slide has at least 12 tumor patches, which means we arbitrarily add 20% probability of sampling tumor patches. For the rest of the patches, we just select a pixel from the tissue pixels randomly. You can see that if the center 128 and 128 region has cancer, we save it to the cancer data directory, and if it's not cancer, we just save the image to the normal data directory. These are the slides I used for extracting the training data. And I saved a copy of the training data in the Google Drive. You can see that in total we have around 400 patches for level 7 training data and around 300 patches for level 4 training data. I split training and validation data. I randomly took about 10% of the training data and put them into the validation directory. It's about 30 images for level 7 and 20 images for level 4 data. Then I trained two Inception V3 models. One model is for level 4 data and the other model is for level 7 data. So as the paper advised, I used the RMS-Pro optimizer, and in my experiments it performs much better than Adam optimizer, and I set the learning rate to 10 to the minus 6. I augmented the data by flipping the images horizontally and vertically. And validation data should not be augmented. And I trained the two models with fit generator for 30 epochs. And the accuracy is around 85%. And I saved the two models to Google Drive. Here I plotted the training and validation accuracy for the two models. This is the accuracy for level 7 model, and this is the accuracy for level 4 model. And then we want to test on a slide and generate the heat map. First I test on the slide tumor 096. So this is the original slide, and this is the tumor mask, and this shows the ground truth. So here we begin to predict the heat map. First I tested to extract an area from the testing slide. One is in level 7 and the other one is in level 4. So then we plot the heat map. To plot the heat map, we need to predict the cancer probability for each small patch in the heat map. So for each row and each column, we extract a small patch from the slide image, and we predict the patches with both level 4 and level 7 model, and then we average the probability of the two models to generate the heat map. In the same time, we also need to save the level 4 patch and level 7 patch to their directories respectively for the future analysis. I also try to use the probability of level 4 model alone to generate the heat map, but the probability given by two models combined performs better. This is the heat map I predicted, and this is the ground truth. And then we want to evaluate my model with the test data. According to the requirements, we should use at least 3 slides to evaluate the model. So I generated test patches from 2 more slides. One is tumor 101 and the other is tumor 110. So I extracted their patches for test data. And now we can evaluate the test data with model evaluate generator. So this is the accuracy I predicted for the level 4 model, and this is the accuracy I predicted for the level 7 model. So these are all my code. Thank you very much.